Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Today we're going to continue talking about numerical sequences, and specifically we will talk about mathematical induction. Let's begin. Definition: mathematical induction is a mathematical proof technique. It's essentially used to prove that a statement P of n holds for every natural number 0, 1, 2, 3, and so on. So what is mathematical induction? It's a mathematical way to prove statements. Let's see how. Now we have steps of the proof of mathematical induction. Let's say P of n is a statement that depends on a natural number n. So it's a statement that is given in terms of n, and n0 is a natural number. To prove that P of n is true for every natural number n greater than or equal to n0, it suffices to verify that P of n0 is true. N0 in this case could be 0, 1, 2. In other words, we need an initial point. So P of 0 is true, P of 1 is true, P of 2 is true, and so on. We suppose that P of k is true where k is greater than or equal to 0. And then we prove that P of k plus 1 is also true. So we have three steps. We need to verify that P of n0 is true. We need an initial point. We suppose that P of k is true. It's true for a certain rank k. And we prove that P of k plus 1 is also true. So we prove it for the next rank. Let's see this number line. In fact, we have two steps for mathematical induction. The first step, as you see here, it's n0. It could be 0, 1, 2, any initial point. We prove that P of n0 is true. In the second step, we have k and k plus 1. We suppose that P of k is true. Then we prove that P of k plus 1 is also true. And here we get the conclusion. Now, what am I talking about? Let's take an example. Consider the sequence un defined by u0 is 0 and un plus 1 is 2un plus 1. And n in this case is a natural number. Now prove by mathematical induction that un is equal to 2 to the power n minus 1. If we just apply the steps before, remember, we need to verify that P of n0 is true. We suppose P of k is true. And we prove that P of k plus 1 is true. So always try to put the question here to see what's going on. We need to prove that un is 2 to the power n minus 1 for every n. So we begin by an initial point, and the initial point here is for n equals 0 because the first value of n here is 0. We could have chosen 1 or 2 or another natural number, but it's preferable to choose 0. Is u0 equal to 2 to the power 0 minus 1? So we replace each n here in the question by 0 and see whether it's correct or not. Well, u0 is 0 from the given here. 2 to the power 0 is 1 and 1 minus 1 is 0. This is true. So we verified that P of n0 is true. The first step is satisfied. We suppose that the statement is true for n equals k. Which statement? This statement, the main question. So we can say that uk is 2 to the power k minus 1. We replace each n by k, and this is a supposition. Supposition means by now it's given. And we prove that the statement is true for n equals k plus 1. In other words, we need to prove that u of k plus 1 is 2 to the power k plus 1 minus 1. This is the question. Now, how do we prove it? We have to use our mathematical knowledge. Let's see. What is uk plus 1 from the given? uk plus 1 is 2 uk plus 1. And then if we replace uk by 2 to the power k minus 1 from here, and then we add 1, we get 2 to the power k plus 1 minus 2 plus 1, which is 2 to the power k plus 1 minus 1. and this is what we need. Thus, we can say that uk plus 1 is 2 to the power k plus 1 minus 1. This is true. Therefore, un is 2 to the power n minus 1. So, again and again, to prove by mathematical induction, we have 3 steps. The initial step, p of n 0, in this case was u0, and then we have the supposition. We suppose that the statement is true for n equals k, and we prove it for n equals k plus 1. Let's take another example. We have the sequence un defined by u0 is 1 over 2, and un plus 1 is 2 un plus 1, where n is a natural number. Prove by mathematical induction that all the terms of un are positive. Now here the question is not that clear. Let's see. The question is to prove that un is greater than or equal to 0. Now, because we need to prove that all the terms are positive, in other words, we translate it into mathematics as un greater than or equal to 0 for every n. So we begin proving by mathematical induction. We begin for n equals 0. We need to prove that u0 is greater than or equal to 0. Now we know that u0 is half, and half is greater than or equal to 0, so this is true. We suppose that the statement is correct for n equals k. In other words, we know that uk is greater than or equal to 0, and we prove it for k plus 1. So is uk plus 1 greater than or equal to 0? This is the question. We go back and see. We know that uk is greater than or equal to 0. This is by supposition. And then if we multiply it by 2 and add 1, we're going to get uk plus 1. We multiply it by 2. This is also greater than or equal to 0. And if we add 1, we get 2 uk plus 1 greater than or equal to 1. And 1, in fact, is greater than or equal to 0. Thus, we can say that uk plus 1 is greater than or equal to 0. And finally, because the 3 steps are satisfied, we can say that un is greater than or equal to 0. Let's see a third example. We have Pn is 2 plus 4 plus 6 plus blah 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 plus 2n for every n belongs to n star. Here we are working in n star. Pay attention. We need to prove by mathematical induction that p of n is n into n plus 1 for every n belongs to n star. So the question here is to prove that p of n is n into n plus 1 for every n. We begin by verifying that the statement is true for n equals 1, because here the first rank is 1. Now, is p of 1 equal to 1 into 1 plus 1? This is the question. And p of 1 means, pay attention, the first term, which is here, 2. So p of 2 would be 2 plus 4. P of 3 would be 2 plus 4 plus 6, and so on. So p of 1 is 2, which is correct. Suppose that the statement is true for n equals k, so I can say that p of k is 2 plus 4 plus 6 plus blah 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 plus 2 into k, and this is equal to k into k plus 1 from here. And the question is to prove that the statement is true for n equals k plus 1. In other words, we need to prove that p of k plus 1 is k plus 1 into k plus 2. Let's see. What is p of k plus 1? Well, p of k plus 1 is 2 plus 4 plus 6 plus blah 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 plus 2 into k plus 2 into k plus 1. Remember, the rank which is just before k plus 1 is k. Well, what is 2 plus 4 plus blah 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 plus 2k? It's k into k plus 1. This is by supposition, plus 2 into k plus 1. And if we take k plus 1 in common, we get k plus 2, and this is true. This is what we need to prove, and this is true. Thus, we can say that p of k plus 1 is k plus 1 into k plus 2. And finally, we can say that p of n is n into n plus 1 for every n. Let's see this application. un is a sequence defined as u0 is 2 and un plus 1 is 4 minus 3 over un. We need to prove by mathematical induction that un is framed by 2 and 3. Try to do it alone. Remember to use mathematical induction, the 3 steps. Well, the question is to prove that un is between 2 and 3, including 2, including 3 for every natural number n. We verify that the statement is true for n equals 0. In other words, we need to prove that u0 is between 2 and 3. In fact, u0 is 2 and 2 is between 2 and 3. This is a true statement. We suppose that the statement is true for n equals k. In other words, we suppose that uk is between 2 and 3, including 2, including 3, and we prove that it's true for n equals k plus 1. So we need to prove that uk plus 1 is between 2 and 3. Well, we know that uk is between 2 and 3, so 1 over uk by reciprocal is between 1 over 3 and 1 over 2. And then if we multiply by 3, we get 3 over uk is between 1 and 3 over 2. And if we multiply by a minus, we flip the boundaries, we get minus 3 over uk is between minus 3 over 2 and minus 1. And if we add 4, we get uk plus 1 is between 2.5 and 3. Now we need to prove it between 2 and 3, and this is in fact correct, because if uk plus 1 is between 2.5 and 3, it will be between 2 and 3. We can add here a 2 because we can say that 2 is less than or equal to 2.5. Therefore, uk plus 1 is between 2 and 3. Let's see another question. Proof by recurrence. This is another name of mathematical induction, that the sequence un is increasing. Well, here it's not that clear. We have to think about the meaning of an increasing sequence. Try to do it alone. Let's see the solution. Well, the question is to prove that un is increasing. In other words, we need to prove that un plus 1 is greater than or equal to un for every n. Verify that the statement is true for n equals 0, so we need to prove that u1 is greater than or equal to u0. Well, u1 from here is 4 minus 3 over u0, which is 2.5, and this is greater than u0, which is 2, so the first statement is true. We suppose that the statement is true for n equals k, so I know that uk plus 1 is greater than or equal to uk, and we prove that the statement is true for the next rank. Is uk plus 2 greater than or equal to uk plus 1? Let's see. Now what is uk plus 2 from here? It's 4 minus 3 over uk plus 1. Is it greater than 4 minus 3 over uk? This is the question. If we subtract 4 from both sides, we get minus 3 over uk plus 1 greater than or equal to minus 3 over uk. Then if we multiply by a minus, we change the inequality sign, we get 3 over uk plus 1 less than or equal to 3 over uk. Then if we divide by 3, we get this quantity, and if we apply reciprocal, we get uk plus 1 greater than or equal to uk. So this statement is true, and we can say that uk plus 2 is greater than or equal to uk plus 1, and therefore un plus 1 is greater than or equal to un. Now let's see together this application. P of n is this quantity, and we need to prove that P of n could be written as n over 2n plus 1 for every n belongs to n star. Try to do it alone, use mathematical induction. Let's see. So the question is to prove that P of n could be written in this form. We try to see it for the initial value where n is 1. Is P of 1 equal to 1 over 2 into 1 plus 1? So is P of 1 1 over 3? Remember, this is P of 1. And if we want P of 2, it means this quantity plus that one, and so on. So it's true. We suppose that the statement is true for n equals k. In other words, we know that P of k is this quantity plus 1 over 2k minus 1 into 2k plus 1. And this is equal to k over 2k plus 1 from here. We need to prove that the statement is true for n equals k plus 1. So is P of k plus 1 equals to k plus 1 over 2k plus 3. Remember, here we replace each n by k plus 1, so we get 2k plus 2 plus 1, which is 2k plus 3. While p of k plus 1 could be written in this form, now the first quantity is nothing but p of k plus that one, and if we replace p of k by its value, which is k over 2k plus 1 plus this quantity, and if we take a common denominator, with some calculations we get k plus 1 over 2k plus 3, which is the required answer. Thus we can say that p of k plus 1 is k plus 1 over 2k plus 3, and we can say that p of n is n over 2n plus 1 for every non-zero natural number. Thank you.